Welcome back to Lesson 2 in our study of the application layer in our course Networks and Distributed Systems based on the book Computer Networking, a Top-Down Approach by Jim Couros and Keith Ross. Lesson 2. Let's begin. Before building a network application, one also needs a basic understanding of how the programs running in multiple end systems communicate with each other. It's not actually programs, but processes that communicate. A process can be thought of as a program that is running within an end system or a host. When processes are running on the same end system, they can communicate with each other with inter-process communication using rules that are governed by the host operating system. But we're not particularly interested in how processes in the same host communicate, but instead in how processes running on different hosts with possibly different operating systems communicate. Processes on two different end systems communicate with each other by exchanging messages across the computer network. A sending host creates and sends messages into the network. A receiving host receives these messages and possibly responds by sending messages back. Even though peer-to-peer is not necessarily recognized as a client-server system, when one peer is requesting an object, it could be considered a client. The peer that delivers the object could be considered a server. As we have just observed, most applications consist of pairs of communicating processes, with the two processes in each pair sending messages to each other. Any message sent from one process to another must go through the underlying network. A process sends messages into and receives messages from the network through a software interface called a socket. The underlying transport protocol used by the processes is the Internet's TCP protocol. A socket is the interface between the application layer and the transport layer within the host. It is also referred to as the Application Programming Interface, API, between the application and the network, since the socket is the programming interface with which the network applications are built. The application developer has control of everything on the application layer side of the socket, but actually has little control of the transport layer side of that same socket. The only control that the application developer has on the transport layer side is the choice of the transport protocol that he wants to use, either TCP or UDP, and perhaps the ability to fix a few transport layer parameters such as the maximum buffer size and the maximum segment size. Once the application developer chooses a transport protocol, the application is built using the transport layer services provided by that protocol. In order for a process running on one host to send packets to a process running on another host, the receiving host must have an address. To identify the receiving process, two pieces of information need to be specified: the address of the host and an identifier that specifies the receiving process in that destination host. That identifier is the socket. On the internet, the host is identified by its IP address. An IP address is a 32-bit binary number that uniquely identifies the host. If everyone does not know at this point that every host on the internet must have a unique address, now's the time to learn. In addition to knowing the address of the host to which the message is destined, the sending process must also identify the receiving process, or more specifically, the receiving socket running on the host. This information is needed because in general a host could be running many network applications, not just one. For example, a single host might hold a web server and a mail server and possibly more. A destination port number identifies a specific application. Certain popular applications have been assigned specific port numbers. For example, a web server is identified by port 80. On a side note, some people often think of a server as being one of the computers over in IT. In other words, the word server is sometimes viewed as hardware, not software. For our purpose, it might be better if we refer to a device, such as that computer, as the host and the application as the server. Because that's in fact what it is. On that same computer, you have a web server and a mail server, two different servers on the same piece of hardware. A socket is the interface between the application process and the transport layer protocol. The application at the sending side pushes messages through the socket. At the other side of the socket, the transport layer protocol has the responsibility of getting those messages to the socket of the receiving process. Many networks, including the internet, provide more than one transport layer protocol. We've already talked about TCP and UDP. When developing an application, one of the available transport layer protocols must be chosen. These available protocols include services along four dimensions: reliable data transfer, throughput, timing, and security. Packets can get lost within a computer network. For example, a packet can overflow a buffer in a router or can be discarded by a host or router after some of the bits are corrupted. For many applications, such as electronic mail or financial applications, data loss can have a devastating effect. For that financial application, either the bank or the customer. To support these applications, something has to be done to guarantee that the data sent by one end of the application is delivered correctly and completely to the other end of the application. If a protocol provides such a guaranteed data delivery service, it is said to provide reliable data transfer. One important service that a transport layer protocol can potentially provide to an application is the process-to-process reliable data transfer. When a transport protocol provides this service, the sending process can just pass the data into the socket and know with complete confidence that the data will arrive without errors at the receiving end. When a transport layer protocol does not provide reliable data transfer, such as UDP, some of the data sent by the sending process may never arrive at the receiving process. This may be acceptable for some applications. Multimedia applications such as conversational audio and video can tolerate some amount of data loss. In these multimedia applications, lost data might result in a small glitch in the audio video, not a crucial impairment. In fact, in these applications, lost data may not even be noticed. Throughput, which in the context of a communication session between two processes along a network path, is the rate at which the sending process can deliver its bits to the receiving process. Because other sessions will be sharing the bandwidth along the network path, and because these other sessions will be coming and going, the available throughput can fluctuate. These observations lead to another natural service that a transport layer protocol could provide, namely guaranteed available throughput at some specified rate. With such a service, the application could request a guaranteed throughput, and the transport protocol would then ensure that the available throughput is always at least that rate. For example, if an internet telephony application encodes voice at 32 bits per second, it needs to send data into the network and have data delivered at the receiving application at this rate. If the transport protocol cannot provide this throughput, the application would need to encode at a lower rate and receive enough throughput to sustain this lower rate. Otherwise, it may have to give up, since receiving part of the needed throughput is of little or no use to this internet telephony application. Applications that have throughput requirements are said to be bandwidth sensitive applications. Many current multimedia applications are bandwidth sensitive. Although some multimedia applications may use adaptive coding techniques to encode digitized voice or video at a rate that matches the currently available throughput. While bandwidth sensitive applications have specific throughput requirements, elastic applications can make use of as much or as little throughput as happens to be available. Catch the term, elastic applications. Electronic mail, file transfer, and web transfers are all elastic applications. Of course, the more throughput, the better. A transport layer protocol can also provide timing guarantees. As with throughput guarantees, timing guarantees come in many shapes and forms. An example might be that every bit that a sender pumps into the socket arrives at the sender's socket no more than 100 milliseconds later. Such a service would be appealing to interactive real-time applications such as internet telephony or virtual environments or teleconferencing, and even especially multiplayer games, all of which require tight timing constraints on data delivery in order to be effective. Finally, a transport protocol can provide an application with one or more security services. For example, in the sending host, the transport protocol might encrypt all the data transmitted by the sending process. And in the receiving host, the transport layer protocol will then decrypt the data before delivering it to the receiving process. Such a service would have to provide confidentiality between two processes, even if the data is somehow observed between the sending and receiving processes. A transport protocol can also provide other security services in addition to confidentiality, including data integrity and endpoint authentication. I think we've kind of gone a little bit over my time limit on this lesson, so let's go ahead and take a break. Take care of any assignments that you may have, and when you're ready, come on back and we'll proceed to the next one.